Welcome to Prelab discussion for experiment 1. The first thing I want to point out is that you need to see the experimental video for the data for this experiment. The way this and other experiments are going to work is that I want you to read through the lab procedure, which is what I have up here, and then extract the data from the video that's presented. In some cases, I might give you the data as a separate sheet, but for this experiment, you're going to watch the video to get the data. I want you to read through this entire lab experimental procedure in order to complete the experiment, but I want it to do an overview of it during this pre-lab discussion and show you some things to watch out for, or some things that are especially important. So that's what we will do now. The purpose of this experiment is to really just familiarize you with common measurements in the lab and common measurements in the chemistry lab. So you're going to be looking at measuring masses, some volumes and temperatures, and then you're going to get a chance to calculate density of a solid and then density of a water. Remember from lecture, density just equals mass over volume. So in part of this experiment, you're going to get a chance to take your mass measurements and your volume measurements and calculate density. This stuff here is important. Gives you some background on the units. Just remember that for solids, we typically look at the units of density in terms of grams per centimeter squared, and then it's different for gases and liquids. Okay, general instructions. I'm not going to read through all of these, but there's a few that I want to point out. The first one is step 2 right here of the general instructions. And you want to watch out for this in the video that you watch. Since we're not actually doing this experiment in the lab, someone else is going to be doing it for you. But watch out to see that they are zeroing the balance that they are working with before they use it, and that the balance is going to read anywhere from out to 2 decimal places to out to 4, depending on the precision of the balance. Higher precision means more decimal places. More decimal places in a given measurement. So, for instance, if you look at here, I'll circle it in purple. You look at the measurement that would come from a balance that gives you out to 4 decimal places. This is higher precision than out to 2 decimal places, which would be lower precision. I didn't use the word precision too much in lecture, but higher precision means, or precision itself is a measure of uncertainty. Higher precision means less uncertainty. Lower precision means more uncertainty. More uncertainty in the measurement. So watch out for the balances that are used in the experiment as Professor Oberth goes through the lab. The third thing you want to watch out for is mainly this part here. When you take a measurement from an instrument, so you take a measurement that's on a balance, or you take something that's electronic, it gives you a number. You don't want to round your measurement. And specifically to this lab, you don't want to round the mass measurement. The reason you don't want to round the mass measurement is because every single digit on that measurement from the scale is significant. In other words, the scale already does the rounding for you, and that last digit is uncertain. So you don't have to read the scale and do any rounding. Just record whatever you see. And that's the two things that I really wanted to point out in terms of some general instructions. The other thing comes down to, let's talk about measuring when we measure volume. And you can read through the instructions here. Part 3 is what I wanted to point out in particular. When you take a measurement from an instrument that's not digital, like a graduated cylinder, or something where you have, like a ruler, where you have to read a scale, you have to estimate the last digit. The way that normally works out is you look at the measuring device that you're using, you look at the smallest unit that it gives you, and then you divide that unit by 10 places, and you estimate to the nearest tenth. The way that it works for this grad cylinder here is that you can estimate out to exactly 1 mil. These are supposed to be mils, so like 15 mils, 10 mils. You can accurately say it's 10 mils or 11 mils, 12 mils, 13 mils, 14 mils, and then what you can do is you can take the 1 mil measurement, divide it by 10, and estimate out to the 0.1. So when you look at this, the volume of water in this grad cylinder, and you read down to the meniscus, which is the bottom of that curve, what you're going to do is say, well, I know it's 12. It's definitely 12 something, 12 mils. And then it kind of looks like to the nearest 0.1, it kind of looks like 12.4 to me. 12.4 mils. But because you estimated that last digit, that 0.4 is the uncertain digit, you would record this as 12.4 plus or minus 0.1, right? Because it could be 12.4 or it could be 12.5 or 12.6. So when you record your measurements, you want to not only record that uncertain digit, the very last one that's estimated, but you also want to write in the uncertainty. The uncertainty is this last, this plus minus 0.01. Okay, let's do it again for measuring temperature, just for practice. So when you're measuring temperature, check out this thermometer. So this thing over here, it's a thermometer. The units are in Celsius. It doesn't show you on the thermometer, but typically on a thermometer, it doesn't show you on this thermometer, but typically on a thermometer you'll have like degrees C or whatever temperature it's in. So when you read the temperature off this, notice that all the graduations on the thermometer are for 1 degree, right? You start at 5, you would have 6 here, 7, 8, 9, and then 10, right? So what you can do is you can accurately say, with certainty you can say, well, I know this measurement, the degree, right? That's where your degree is raised to, the top of that black line. I know that degree is 8 something, and then what I'm going to do to estimate the next digit, the 0.1, is say, well, if I take 1 degree, which is the difference between 8 and 9, and then I divide it by 10, that means I can get to the 0.1. So I could say this is like 3. Looks like 8.3 to me. But it could be 8.3, or it could be 8.4, or even 8.2. In this example, it tells you somebody estimated it and said it looked like 8.3, 8.4, or 8.5. But it's possible that you said, well, it's 8.3 plus or minus 0.1, right? There's really no exact answer. You just want to get in the ballpark, right? Some of you might look at that and say, it looks like 8.2 to me. So really important, what I'm trying to highlight is the importance of estimating that uncertain digit and how we estimate what that uncertain digit is. It's that we get all of the certain numbers from what the scale tells us, and then we can estimate one more to the right. And that's what's going on with the volume measurement and the temperature measurement here. So practice that. As you go through and you record the measurements from this experiment, practice writing down those uncertainties and trying to get them so that I can look at it and hopefully give you some feedback. All right, so there are 5 parts to this experiment, and I'm not going to go through all of them. The first one, or I'll go through all of them, but I'm going to let you read them in detail yourself. So the mass measurements, essentially in lab, what you would have done is taken 6 random things between you and your partner and gotten the masses. What Professor Oberth does is she does this for you. There's going to be 6 things that she'll take the mass of. You want to record, again, all of the digits that you see for each of them. Part 2 is just some temperature measurements. And this part's actually kind of cool. You would have taken the temperature of just some water, and then you would have heated some water, taken the temperature, and then added some ice ultimately and taken some temperature. And you and your partner would have taken a measurement and then compared them to see how people can interpret reading the scales slightly differently. That is the purpose of this part. So in this part of the lab, watch the video, get the data. And then actually part 4 here is the one where you look at the addition of salt to water and see how that affects the temperature. Density. So for the density part, you're gonna have taken the mass of water, and you'll take the volume of water, and you'll figure out what the density is. That's part A right here. So the density of water is going to involve getting the volume. It kind of gives you the instructions on how she's going to get volume in the graduated cylinder, getting the volume, getting the mass, and then taking into account, again, density equals mass over volume, and then you can calculate the density. So watch out for the mass measurements and the volume measurements of water in order to calculate the density of water. All right, so the one that I wanted to highlight, though, is the density of a solid metal object. Sometimes it turns out that, so you can get the mass of your solid metal object, and then in some cases you can measure the sides of your solid metal object. For instance, let's say you had a nice rectangular solid metal object. I'll try to draw a better rectangle for you. You have a nice rectangular solid metal object, and it's like, I don't know, it's 1 by 5 by 1 centimeter, right? You could say the volume equals length times width times height, and you could get the volume. And then you would say, well, I measured the mass, I calculated the volume, therefore I can just get mass, right? Or I can figure out what the density is. Sometimes you have to deal with an irregularly shaped solid, and you have to determine the volume of your metal object by the displacement method. And Professor Oberth is going to show you the displacement method in the video, but I wanted to show you what it is just for a second. Okay, so the way that it works is the displacement method works off the principle that, objects thrown into water will displace a volume of water that is equal to their volume, right? This is you might experience this if you sit in a bathtub. You notice it mostly in a bathtub. You sit in the bathtub, the water rises. If you didn't touch the bottom of the bathtub and the water just kept rising and didn't spill out, the amount of water you displaced would be your volume. Okay, so the way this works is you take a graduated cylinder. That's this thing, a grad cylinder, with some initial volume of water. Volume initially in the flask. It doesn't really matter how much you add. Usually like halfway up the grad cylinder is what you want to aim for. But you have some volume of water. to start, you want to write down that initial volume, and then you're going to take your marble. Let's say you have some marble whose volume you're trying to determine. You're going to take that marble and you're going to throw it into the flask, right? When it touches the bottom of the flask, that water is going to rise. So this is like after adding the marble. That water is going to rise. Let's draw in our marble down here. And let's say, the water rises to up to this point, right? This is your final volume. Your final volume. The difference between the two, the VF, your final volume, VF, and then VI, your final volume minus your initial volume equals the volume of the marble. The marble, or whatever object you're trying to get the volume of. So it's essentially, it's like this area here, right? This is your marble volume. So when she does this in the video, she'll do this for a variety of solids. This is what she's doing. For those of you that are curious and maybe wanted some more detail. The thing I'll point out is that, remember, so with solids, you want your mass to be you want your volumes to be in centimeters cubed, right? Remember that 1 mil equals 1 cubic centimeter. So the measurements on this graduate cylinder will be in terms of mils, but you can report them in terms of centimeters cubed. All right, just a couple last things. So that's this part B. The last thing is specific gravity, which doesn't require a lot of explanation. Specific gravity, I'm going to let you read through all this, but essentially what it does is it allows you to evaluate the amount of dissolved solid in a liquid. And in this lab, you're going to do it for urine, for synthetic urine. Specific gravity itself takes into account the density of whatever substance you're looking at, which in this case is urine, and compares it to the density of water at the same temperature. Because urine is mostly water, what you're doing is you're controlling for the density of water in urine, or the water in urine, and it allows you, specific gravity measurements allow you to see what the amount of dissolved solid is, and then compare them. All right, and then here's some questions you can answer for that. The last things you want to do is make sure you answer the final question on, what did you learn from the experiment? And that's it, folks. So check out the lab. Watch this video to get an overview of just going through the experiment, and then watch the experiment for the data, and let me know how it goes and if you got questions.